So sorry about yesterday. Hopefully a decent number of you got the email before you came. They don't want to post anything on the doors anymore, so I would just check email before you leave the house or whatever. Because I will email you the minute I decide I ain't going. Yesterday was definitely a I ain't going situation. So I feel much better today, obviously. I think last time we got into dividing radicals. I did a little preview of section 10.4 or 10.5, which is making radicals like terms. We did a little bit of a preview of that. We're going to get deeper into that today. First thing I've got to do is finish out section 10.4, which involves something called rationalizing the denominator or the numerator. I don't know why I was saying it. So if you break that word down, rationalize, and this is not the English definition of rationalize, something we can all do all the time. So if you know what rationalize means, you know we do it all the damn time. This is the math version of rationalize. What does rational mean in math? Rational. In English, we have a lot of situations that are easy to tell that they are not rational, especially nowadays. But in math, what does rational mean? Rational numbers, rational expressions. Oh shit, let me ask you. All right. This will be a drinking game. I drink every time somebody answers a question. I will remain sober. So, rational numbers, rational expressions. What's the root word of rational? Root word of rational is ratio, which refers to what kind of a number? Fractions. I like it. Okay. And rational versus irrational is the more important. So rational numbers are the ones that can be written as ratios of whole numbers. Remember that? What were the irrational numbers? They were the ones that were like pi, square root of 2. They're irrational. So square roots of numbers that I can't do the square root of, like square root of 7. Any root, cube root of 9, I can't do that. That would be an irrational number, meaning it's a decimal that goes forever and doesn't repeat. Oh shit. You with me? Alright, how's everybody doing? Okay. So like square root of 9, is that irrational? Square root of 9. Is that irrational? No, because square root of 9 is 3. It's not a decimal that goes forever and doesn't repeat. It's 3. I like it. So, rationalize. Let's start with denominator. Holy crap. Let's zoom out a little bit. Okay. So tell me, why is this expression, why is it not rationalized in the denominator? Can I do the square root of 8? No, so officially that is an irrational term. I can't do the root, so it's irrational. So I really want this to make a ton of sense. I want to multiply this by something that completes the root on the bottom. So what do I mean by that? Why can't I do the square root of 8? It's a really weird question, but why can't I? Okay, it's one good thing, but more importantly, like, why can't I do the square root of y squared? If I assume it's not negative and bullshit, right? Why can't I do the square root of y squared? What is the square root of y squared? I like it. Why? I love the absolute value people. I love it, but I said no negative numbers were used, to protect the innocent. Square root of y squared would be y. Are you guys with me? Why am I able to do the square root of y squared, but I'm not able to do the square root of 8? Because y squared has 2 y's in it. Kick ass. So what is the bottom missing? Another a. I like it. So what do? I multiply top and bottom. I don't multiply top and bottom by a. Why wouldn't that do anything for me if I try to multiply by a? Can I put these together?
No.
So of course I've got to multiply top and bottom by square root of a. And this is a beautiful idea. What is square root of a as a power? A to the 1/2. Thank you. A to the first is just a. Square root of a is half of a, right? So if I multiply by another half of a, I make a whole a. Oh. Do you guys understand? So this is what rationalization means. I prefer the term complete the root. What does that root require? Two things. What does it have? One thing. What do I give it? Another thing. Right? So what do I get on the bottom now? On the top, what do I get? 2 square root of a. Good. I can't put them inside because it's not the square root of 2. And on the bottom, I get square root of. And pretty much this whole section is going to say assume there's no negatives used. Just because there's a lot of other stuff to worry about besides the absolute value. So what do I get at the bottom then? A. Can I cancel these? Yay. No. Of course not. They're not both in the radical. Kick ass. So is the bottom rational now? Meaning no radicals present? Yes. That's what rationalizing denominator means. Give it what it's missing until it becomes no radicals anymore, no roots. So what if, okay. What if I had this here? Yeah, let's make it, yeah, I like it. That's a Y, by the way, is that cool? Probably the worst letter I could pick, but oh well. That's a Y. Okay, so again, this is, do you guys start to see why I call it complete the root? What does that root on the bottom require? How many things? Yes, ma'am?
Is that 3 and then the square root of y, or is that the cube root?
Oh, I got you. That's the cube root. Yeah. So what does the bottom require? How many things inside does it need? 3. Not how many more. How many total things does the bottom need? 3. How many things does it have inside right now? 1. It's got a 2, right? So how many more 2's does it need? 2 more. It's beautiful. You don't now the problem with me doing that first example, I always forget. I always want to try to start with a cube root or something, because people see that first example and they say, oh, just always multiply by what it is. No. Why did that work on the first one? Because it was a square root. So of course it just needs itself to complete itself. But number 2, it needs 3 things. It's only got 1 so far. So what do I got to multiply top and bottom by? Yeah, cube root of 2 squared, or 4. The other 2 2's. That's why Y was such a poor choice of letter, but oh well. So at the top, what do I get? Cube root of 4y. And the bottom, what do I get? I get the cube root of 8. Now, if you're smart, you can skip that step because I designed it so that it's able to be done. What is the cube root of 8? 2. Bless you. All right, please see how that just insanely makes sense. Why am I allowed to give it what it's missing? Because I have 2 sides. I have the bottom and the top. Why am I allowed to multiply an equation by something? Because I have 2 sides. I can balance it. Here, a fraction, I've got 2 sides, the bottom and the top. I'm allowed to do stuff because I can balance what I do. Maybe. So what about this here? You guys try this one. Pick some better letters. B is a good one. There you go, Jeff. I'll give you a little hint. Don't look at the bottom as if you have 1/16. That's silly. Yeah, the bottom is 4 2's already. You guys see that? 16 is 2 to the 4th. It's 4 2's. All right, now go from there. Say to yourself, how many more 2's does it need? And then you give it to it. It's crazy. So what do you multiply top and bottom by? Fifth root of 2. The root's got to be the same, right? So the fifth root of 2. Fifth root of 2. And again, why did I do that? Because right now it's already got 4 2's. It's a fifth root, so how do I complete the root? I give it one more 2. That's why I love the phrase complete the root rather than rationalize the denominator. So what do you get on top? And of course on the bottom I'm going to get 2. I'm going to get fifth root of 2 to the 5th, which is, bam, 2. You designed the bottom to come out that way, so of course it's going to come out that way. I like it. So another way to look at this, let me see if you guys get this. This is 4/5 of a 2. Let me say this again. This is not a whole 2. This is 4/5 of a 2. If you put 2 to the 4/5 in your calculator, you're going to get a number smaller than 2. So this is, in fact, what is this as a fractional power? 2 to the 4/5. So it is 4/5 of a 2. So if I give it 1/5 of a 2 more, it becomes a whole 2. I mean, that's a beautiful idea. Okay, maybe. All right, let's try one more of these. What about this here? 7th root of 2x over. Oops. I like it. Just sit close to her. Bless you. Okay. So what do you guys multiply top and bottom by? Good, because we got 4 A's. I need 3 more. Yeah, I got 2 B's, so I need 5 more. So the top just gets mushed together. Okay, so I get 7th root of 2a cubed b5x, just putting in alphabetical if you want to. You don't have to. And on the bottom, I am going to get ab, because it becomes 7th root of a7 b7. Where'd it go? There it is. Whoa, Jeff, I'm really zoomed in. So on the bottom, I completed the A and B, so I can do the 7th root of both. Bam! And on the top, I just slam all that stuff together. Okay, it really actually is that nice. Yes, sir?
So this doesn't matter? Like, the top doesn't matter, it's just the bottom?
Yeah, you're focused entirely on the denominator. It's like when I'm adding fractions. Do I care what the tops are? No, I don't give a shit. It's all about the bottoms making them the same. I love it. Now, if the instructions say rationalize the numerator, you do everything we just did, but then you focus on the top. It's the same work, right? So, just to do one of those, just in case. So if I said rationalize the numerator, and I've got, let's do something a little bit different here. 4th root of what you got, Jeff? 4b7. My God. Okay. My My writing astounds me. So this is a little bit different. Let me see if you guys can key in on this. You could really make this problem really hard. Don't do that. You see how there's already like more than enough B's, but there's still actually not quite enough B's on the top. How many B's do I need on the top? How many more B's? How many more?
We don't need B.
Yes, we do.
One.
One more B. Why? Because then I can take the 4 through to B8. Right? So it's more than just making it exactly the same. It's make it a multiple of the root, because then I can do the root. So hopeful. Do you guys see that? If I would have just been a B8, it would have been so stupid easy. What is the 4 through to B to the 8th? What is the 4 through to B to the 8th? B squared. 4 goes into 8 twice. And how many, is it missing 3 more 4s?
Yeah.
No.
No, just
It doesn't have just one 4, it's got
two.
2 2s. Always break it down if you can. So it's got 2 2s. How many more 2s does it need?
Two.
2 more.
4.
And then it needs 1 more B.
Yeah.
So why am I looking at the top now? Because it told me to. Right? The instructions will tell you which one to focus on. Okay, some of you guys look concerned. Okay. So what do I get on the top? Let's just write it out. I get the 4th root of 16, B to the 8th. And on the bottom I get the 4th root of 12, AB. So what is the 4th root of 16? 2. Takes 4 2's to multiply to 16. 4th root of B8. Yeah, 4 goes into 8 twice. And now the bottom is the one I don't really care about because it told me to focus on the top. I like it. Normally we rationalize denominators because radicals are gross already. They're even worse if they're on the bottom. But there are situations in later math when I want to rationalize the numerator. It's the same idea. Okay, maybe. How you guys feel about that? It's not a horribly evil idea. It's beautiful. If you just remember, complete the root. What does the root need? So how many more do I have to give it? It's a beautiful idea. No, some of you guys are like, you don't know the word beautiful, Jeff. Let me get you a dictionary. Beauty's in the eye of the beholder. Leave me alone. All right. Enough of that. Let's get back. I want to do this kind of problem. Just to remind you guys how this works. So if you need to, let's see, I want to get you so used to the shortcuts because it's so stupid beautiful. Again, that word. What is the shortcut here? How can I do the shortcut? 5 goes into 8 once with 3 left. 5 goes into 31 6 times with 1 left. 5 goes into 2 0 times with both left. Now, let me show you why that works. That's so nice. Well, now, one reason why I should expect it to work sort of like that is because a 5th root is also a what power? 5th root is a 1/5 power. So I am dividing by 5. It is 1/5 of those powers. But a more direct way to look at this is a to the 8th is a5 times a3. B to the 31st is b30 times b. And c squared is this poor little c squared. Do you see these? They're there. And this one too. There you go. They're all left because I can't do it. But these I can do the 5th root of. Right? 5th root of a5 is a. 5th root of b30 is b6. But why do this step when you're effectively doing the same math? You just got to know how to do the remainder. You should be able to do that part in your head. It's just the extra shit on top of what would be a nice number. What would have been a nice number? 5. So how much extra a's? 3. So they get left. And that's a lot like when I do something like square root of 98. How would I do that? Don't be trying to do square root of 98 in your head, because you can't. What's the square root of 100? 10. So the square root of 98 is a little bit below 10. But I want a more exact answer. How do I do this problem? What square number goes into 98? What's 98 divided by 2?
49.
Right, so this is the square root of 49 times the square root of 2, which is 7 rad 2. I don't know what rad 2 is, but I know what square root of 49 is. That's what it means when it says simplify radicals. I kind of call it reducing a radical. Not really that, but oh well. Makes sense to me. Do you guys remember that we did a decent number of these? We did a whole sheet of these. So what about this here? What about the cube root of 40? What kind of numbers am I trying to divide into 40 now? Not 4, it doesn't matter because it's a cube root. So what kind of number do I use? 8 and 27 and so, but 8's good. 8 goes into 40 5 times. So I can break it up. This becomes the cube root of 8 times the cube root of 5. What's the cube root of 8? 2. What's the cube root of 5? I don't know. I like it. I like it. Really, now Jenna had a good point earlier. Number one, you don't want to forget this dude. Cube root can't suddenly go away and make it become a square root. You can't do that. But also make it really clear to yourself and others that that is a root, not a coefficient. So I got to be careful how I write it too. Okay, maybe. Okay. Now, to get back into what we sort of got into before, this is, I think, section 10.5, I think. I'm not sure. I don't know sections, I just know ideas. Leave me alone. So tell me, let's start off with a nice one. What is the cube root of 7 plus 4 cube root of 7?
5.
Yeah.
5.
So, what is the cube root of 7?
343.
Say again?
Wait, sorry.
No. Not 7 cubed. I love Mark is right there. He's like, yeah. Cube root of 7, I have no freaking idea. I can estimate it. I can use a calculator, but I don't know what the hell it is. So it acts just like an x for a lot of things. Something I don't know plus 4 more of those same things I don't know is 5 of those stupid things I don't know, right?
Yeah.
So this is 5 of these. Bam. Again, it's like terms. Where do we go? Who's? Okay, I love it. I love it. Please ask questions, my God. I can see a lot of you like, this is my life. No. Be like Sumi. So, are you cool with something I don't know plus 4 something I don't know is 5 something I don't know, right? So what if I would have used an m here? M plus 4m is still 5m. Whatever I use, if I use the same thing, I could just collect them. So what if I use this? Do I know what that is? Oh, good. All right. I'm going to go person by person now. So I got one thing I don't know, cube root of 7, plus 4 more of that same thing makes how many of that thing? 5 of that thing. Now I know when you first look at it, it looks wonky, but it's the same idea as like terms. These are things I don't know. So I can collect them, like always. That's what this is. It's just collecting them. So I don't have, I got X's over there and X's. No, just get all your frickin' X's together. Put it in a bag. Put it in a bag somewhere. Is that too easy? It's just for me. So if I had, for example, the 8th root of 5 minus 2 8th root of 7 plus 8 8th root of 5. Where are your like terms? These are like terms. So I got one of them plus 8 more of them. 9 of
Negative 2.
minus the thing that had nobody to go with. Poor little dude. Same shit as always. This is just like x. This is just like x minus 2y plus 8x. It's exactly the same problem.
So the index doesn't matter?
It totally matters. Why was I able to add these together? Because they were like terms. So,
All of them are a root of 8.
totally. I love it. So that doesn't make it like. So here's the idea. If the inside's not the same, they're obviously not like. They're not like terms, right? 8th root of 7, is that the same thing as the 8th root of 5? No. But also, what if I had square root of 11 plus cube root of 11? What's that? That. I'm done. They're not like terms. Is that cool? You can only say I've got this many of these if these are all exactly the same. It's the same idea as if I said, what's x plus x squared? Now, some of you guys don't think you're going to say something wrong, but what's x plus x squared? Yes, that. They're not like terms. Yes?
So in order for you to combine, like for them to be like terms, they have to have the same
Index, the same root, and the same inside. They have to be completely the same. So here, they have the same base, don't they? But why are they not like terms? Because they don't have the same exponent. They're not the same number of x's. So it's very similar to the requirements for like terms with variables. Okay, it doesn't just have to be the same letter, it's got to be the same amount of each letter. It doesn't just have to be the same root, it's got to be the same inside also. Oh shit. Alright. So, here's the next level of this. So what is the square root of 28 minus 2 square root of 7?
28 is 4.
Yeah, so right there, this is not some number of square root of 21 or something. You guys see where somebody might come up with that? Holy shit. You can only combine them if they are like. Are these like? No. They're like not like. Like totally. So, what do I do with 28 then?
4 times 7.
Yeah. 28 is square root of 4, square root of 7. Square root of 4 is 2. So this is 0. So square root of 28 is the same thing as twice the square root of 7. They cancel each other out because they're the same thing. So you must have like terms, but they aren't letters. If the letters are not the same, you can't do shit. Right? You can't take the x and erase one of its legs and make it a y. It's not legal. But with radicals, they are numbers. Maybe I can do something with them. Maybe I can simplify them and then have like terms pop out at me. So what about, let's see, cube root of, what you got, Jeff? I don't know, man. Yeah, cube root of 56 plus 2 cube roots of 7. I love you guys. Whisper. You guys see how these problems very often have a hint in them? What's the hint in this problem? In order to be like terms, what number must I be left with in that first guy? A 7. So maybe try 7 into 56. Do you guys, I mean, there won't always be, and sometimes they might be misleading. Maybe they won't end up like terms, but I'm going to try freaking 7 first. And 7 times what is 56? 8. And what's beautiful about 8? It's a cube. So this is the cube root of 8 times the cube root of 7. Become a 7. Plus 2 cube root of 7. What's the cube root of 8? 2. So 2 cube root of 7 plus 2 cube root of 7? 4. Cube root of 7. Okay, maybe. Well, can you always make them like terms? No. So, yeah, that little trick I just did will not always work. But if it's going to work, then that will work. If it doesn't work, then it's like, I'm not going to be able to put these things together. Let's see. What about this guy? Which guy, Jeff? Yeah. This is a little bit strange, but that's why I want to show it to you. You could sort of make like terms here. I'll show you that one last step that's a little weird. Again, there's a beautiful hint over here. So how do you break up 54?
27 times 2.
And how do you handle cube root of x to the 4? Yeah, 3 goes into 4 once with 1 left. I like it. So what's cube root of 27?
3.
3, and you have an x there.
X.
Now it looks like you can't go any further, and in one sense you're right, so I'm not going to be overly angry if you don't go one more step. The next step you could sort of take, it's a little bit weird, is you can factor out a cube root of 2x. Which, to be honest, is what we do when we combine like terms. I mean, what is 4x minus 2x? What's 4x minus 2x? 2x. Because if I take an x out, 4 minus 2 is 2. I mean, that's the step that we always skip because we don't need it anymore. Maybe when you first were taught this, you saw it like this. I don't need this step anymore. But here, I need it because these are not like themselves. But at least I can take that cube root out. All right. Okay. Oh, cool. I like that. How do you guys feel about that idea of combining radicals? Not that was really beautiful is you normally can't do anything if they're not like terms, but with radicals maybe you can do something to force them to be like terms. Let me ask you, what do you think? Let's remember this, recall. What is the square root of 5 times the square root of 7? Square root of 35, I love it. Why am I allowed to do that? They're both square roots. So they're both the same root. I love it. Kick ass. So what's this? I don't know why people have trouble with this idea. Oh my God, Roman numerals and art. Just deal with it. People always have trouble with recall this. Let's go further back for this next one. What is 4y times y?
4y squared.
4y squared, I love it. So what is 4 rad 2? Oh shit. What is 4 rad 2 times rad 2? 4 times rad 4,
So,
which is 4 times 2, 8. So you don't worry. Now look, did I care at all about that 4 in this problem up here? No. The y and the y can go together. So what can I do here? Can I do anything with that 4? No, there's no other number. But the rad 2 times rad 2 I can do. People always freak out about that, but it's the same thing we've been doing with variables forever. I don't care about the coefficient if there's only letters after that. That's all I care about. Put those things together. So what do I do with, let's see. What about this guy? 2 rad 7 times 3 rad 3 minus 4 rad 5. Oh, yeah. Oh, shit. Sorry. What property, what property am I going to use here? More specifically, distributed property. Again, properties don't give a shit what's in the problem. They don't care. They don't care. It says if there's something in front of a subtraction problem, in parentheses, I distribute that something. I mean, it doesn't care there's radicals in there. We do. But the process don't give a shit. What is 2 rad 7 times 3 rad 3? Well, what can I put together?
6.
Yeah, the 2 and the 3 is 6. Rad
21.
21.
8.
Yeah, 8. Rad
35.
35. Now, please, dear God, why do I know it doesn't make any sense to try to simplify those radicals? Because I know 21 is 3 times 7. It's not 2. I know 35 is 5. I already saw what the hell they came from. I know there's no point to try to break them down. There's only one of each thing inside, and why would I waste time? I'm the one who made them. I know what's in them. Please, dear God, don't go one more step. There's always people like, I gotta go one more step. I don't know what the hell they were put here. 14. There's no like terms there. Don't go further. Here, you guys try this one. Yeah, it's beautiful. All right. There's that word again. Inconceivable. I do not think that word means what you think it means. So you guys are like, I ain't doing that. Math boy's going to do it in a minute. You just, in general, you just take each piece as it comes, right? You don't look at the whole damn thing at once. The people that are really good at math kind of naturally look at the parts. They don't look at the whole thing. That was me. I was just lucky. I could just see the parts and not give a shit about the whole thing. I think people that are not so good, they just see the whole thing like, oh my God, there's a lot of shit. So, here, what do I get there? That's all I care about at first. 10,
10.
rad
10.
10. That's kind of nice. It feels like you should be able to do some of that, but you can't. And then I get here,
Negative 20.
negative 20, rad
4.
4. We'll worry about that later.
Plus 6.
6, rad
35.
35.
Negative 12.
Minus 12, rad 14. Each of those little problems were easy. And now I just look through to see, is there any like terms or anything I can do anything with? Yeah, this will be 10 rad 10, 20 times 2. Are there any like terms? No. Anything else I can simplify? How did that become a 20, Jeff? I don't know, man. Shit. Anything else I can simplify? No. Any like terms? No. Done. It just feels like it's not done, but there's these radicals. There's not going to be as many like terms. All right, one more. Uno más. I'm like a politician that uses my only phrase I know. Here, this is a neat one. Part of your brain should tell you something interesting should happen here. Because, well, let's see. Try it out, and then we'll see if anybody can tell me why you should expect what happens to happen. Is this number rational or irrational? It's so irrational. And that one is equally irrational. So what you get at the end is most intriguing. So try. Now, I want you guys to get to the point where if I see square root of 3 times square root of 3, the answer is square root of 3 times square root of 3, the answer is 3. Half of 3 times half of 3 is a whole 3. Square root of 11 times square root of 11 is 11. Square root of 48.7 times square root of 48.7 is 48.7. Bam, bam, bam. Now, you could write square root of 9 and waste time. But I want you to get to the point where you see square root of 3 times square root of 3, it makes a whole 3. Just cut to the chase. Right? So what do I get here? I get, 4 times 3 is 12. And then here I get minus 2 rad 15. Plus 2 rad 15. Minus
27, 5.
root 25, okay, 5. Rad 5 times rad 5 is 5. So what happens in the middle?
0.
And 12 minus 5 is?
7.
Holy shit, that ugly ass number times that ugly ass number is 7. That's kind of neat. What's up? 12 minus 5.
I got negative.
Neato. Shouldn't. Alright, that's it. Oh. No, it's 4 square root of 9. Even then, it would be even bigger. Positive.